Hello everyone, welcome to my channel. This is Rekha Venkateshwarlu, Assistant Professor of Physics, Government Degree College for Women, Nalgonda. In the present class, now I am going to present the topic equation of continuity as a part of electromagnetic induction. This is BSc Physics 5th semester Electromagnetic Theory paper, Unit 3 syllabus. My plan of talk in the present lecture is introduction, current density, J bar. Then after we will discuss the concept of drift velocity. After that, relation between current density J bar and the drift velocity BD. After that, equation of continuity, and lastly, we will see the important points of this lecture. So before start of actual discussion equation of continuity, so let us discuss some important basic terminology regarding this. What is current density? Right? Current density is nothing but the amount of current passing through the unit surface area normally at any point across cross section of the conductor. So for example, if you consider, wait, so this is a conductor, right? Imagine that this is a conductor, okay? Now the current is passing through this conductor from the first end to second end, from the left end to second end. So now this will be the cross-sectional area, right? The amount of current passing through the conductor per unit area. Per unit area normally to the cross-sectional area. So amount of current passing through unit surface area, that is 1 centimeter square. Normally through the unit surface area is called as current density. The current density is a vector quantity. It is expressed as J is equal to I by A. I by A, amount of current passing through the conductor by cross-sectional area of this conductor. So here it is circular cross-section. So that based on shape of the conductor. Okay, it is a vector quantity. Its direction is the direction of positive charge at that point. Okay, now you see here. So this is the current carrying conductor, right? So for example, simply you take the metallic conductor, then the cross-sectional area is like this. If their total cross-sectional area, we are dividing to small area elements, right? You consider a small infinitesimal area element ds bar. The direction of ds bar, how it is perpendicular to this area element. It is shown by the arrow mark. Right. Now the current is flowing through this small area element direction di bar. That is the direction of j bar. The direction of current at this point is along the direction of j bar. The direction of area element is what? ds bar. Then the component of ds bar along the j bar would be ds cos theta. So then the amount of current passing through this small area element is given by J into ds cos theta. We write it as J bar dot ds bar. So this di is equals to J into the area element component along the direction of J bar. That would be ds cos theta. J into ds cos theta gives J bar dot ds bar. So therefore, di equal to J bar dot ds bar. Then this is the current passing through this small infinitesimal element ds bar. Then the total current passing through this whole conductor, through this total surface area coming out is given by integrating that di. We get I equal to surface integral of j bar dot ds bar. The second figure you observe that, so these are the charge carriers, right? Generally conventional current direction, what we take, the direction of flow of positive charge, they taken as the conventional current direction, right? Here the positive charge carriers are moving in this direction. Okay. Now, on this cross-sectional area, I considered a small area element ds bar. So the direction of ds bar is like this, right? So these charge carriers are moving with the speed v bar along this direction. Okay, along this direction. Now the direction of the movement of these charge carriers, that is the direction of their drift velocity, we will discuss later that one. Okay, so what I'm saying, the current density is nothing but the amount of current passing through unit normal surface area is called as current density. It is a vector quantity, right? Its direction is opposite to the motion of the electrons at that point. Actually, when the metallic conductor or any conductor is connected to the terminals of the battery, then the charge flows from positive terminal to negative terminal in this direction. For example, it is connected to the positive terminal, the second is connected to the negative terminal, then the electrons flow from negative terminal to positive terminal, but the conventional current direction is taken as the direction of flow of positive charge. So here current direction is positive terminal to negative terminal. The electrons movement is from negative terminal to positive terminal. So electron movement is from the second end to the first end, but the direction of current is from the first end to the second end. So the direction of positive charge is from left to right. So this is the direction of J bar. So that the direction of J bar is the direction of the flow of positive charge, or it is opposite to the motion of the electrons at that point. Since J is equal to I by E, its SI unit is ampere per meter square, right? So then you can write the dimensional formula, ampere E by meter square L square, then you will get EL minus 2. Okay. So vectorially we write the expression for I, already I explained, I equal to surface integral of J bar dot ds bar. How we are writing? J bar dot ds bar represents the amount of current passing through the small area element ds bar, then the total amount of current flowing through the total cross-sectional area of the surface S is surface integral J bar dot ds bar. Okay. So what is the difference between current density and current? Right. Current, how we define the current? It is the rate of flow of charge. I is equal to dq by dt, or I equal to charge q by time. We take that one. Current density, how we are defining? It is the current per unit area normal to the direction of drift velocity of the electrons, right? I equal to surface integral J bar dot ds bar. Okay, here J bar equal to I by A. It is a vector quantity, current is a scalar quantity. Since here we have taken the dot product, the dot product of current density and area vector, the dot product always gives the scalar quantity. Current is the scalar quantity. It doesn't obey the vector addition laws, but J bar obeys the vector addition laws. The direction of J bar is along the direction of drift velocity of the positive charge, or opposite to the direction of flow of electrons. So current density is a vector quantity, current is a scalar quantity. The SI unit for current density is ampere per meter square, and the SI unit for current is ampere. Okay, this is the difference between current and current density. Now, let us discuss about the drift speed or drift velocity. What is the drift velocity? It is defined as the constant average velocity attained by the charge carriers when the electric field is applied across the conductor. Yes. So let us discuss this concept in detail. Just imagine that this is a metallic conductor. Now, the first end is connected to the positive terminal. The second is connected to the negative terminal of the battery. Okay. So then we are applying some potential difference across these two ends. We are applying the potential difference across these two ends. So you have to, at the left finger, the positive potential, at the right finger, the negative potential is established. So due to the potential difference applied across the ends of this conductor, now charge starts to flow from the first end to the negative end. But actually what happens here, in the metallic conductor, electrons flow from negative end to the positive end. Then the positive charge flows from first end to the second end, that is the left end to the right hand. Electrons flow from right hand to the left end. Okay, right. So before applying the potential difference, so in the absence of connection to the battery, then the free electrons inside the metallic conductor move randomly, right, with the different velocities. Their average speed is in the order of 10 power 5 meter per second. That is due to the thermal agitation, the free electrons contain the speed 10 power 5 meter per second average thermal velocity. So with that speed, the free electrons move randomly inside the volume of this conductor. Okay. So then the average thermal velocity will become zero. For example, if there exists a number of n number of free electrons and they are having the different thermal velocities at any instant of time, v1 bar, v2 bar, v3 bar, and so on, then average thermal velocity we write v1 bar plus v2 bar and so on, vn bar all by n. That will become zero because the electrons are moving randomly. So one electron will go in this direction, another electron move with the same speed in opposite direction, they get cancelled. So like that, the average thermal velocity of the free electrons will become zero in the absence of electric field, right? So whenever we apply the potential difference across these two ends, then these free electrons will attain the constant speed. That constant speed is called as drift speed. So when the conductor is connected to the terminals of the battery, or when the potential difference is applied across the ends of the battery, these free electrons attain a constant speed. Then they will move with that speed, they drift with that constant speed. Okay, that speed is called as drift speed. So the velocity is called drift velocity. Okay, so the drift velocity, due to the drift velocity, the electrons move like this curved path, like as shown in this figure, like this one. Why? Because the concept is when it is connected to the terminals of the battery, right, of the battery. So then electric field is we are applying across these two ends. Here the positive potential, it is the negative potential. So the electric field strength direction is plus 2 minus. In this direction, electric field strength is establishing, right? Now, the electrons are moving from minus to plus. So electrons are moving opposite to the electric field strength, right? So they acquire the acceleration A equal to minus E bar, minus small e, capital E bar. E is the electric field strength. Okay. So due to this acceleration that is acquired by the electron speed will increase further. So the increase in that speed is very less value, of course, but these electrons are subjected to the frequent collisions with ions or atoms of that metal. Therefore, in that collision, they will lose that increasing speed. So they will lose the whatever the kinetic energy gained due to this acceleration. The kinetic energy or the speed gained due to the acceleration or due to the electric field will be lost during the collision. Again, in the next collision, their speed increases, kinetic energy increases. Again, that will reduce or that will decrease in the next successive collision. So apart from the thermal velocity, so due to this electric field, it is having some more velocity. It is gaining some more velocity. So resultant of this, the charge carrier, that is nothing but electron, is following this curved path. So therefore, electron moves or drifts like this curved path as shown in the figure, right? Now, let us derive the relation between drift velocity and current density. So consider a conductor of length L and a cross-sectional area capital A. It is connected to the battery of EMF some V volts. Okay. Since the first end is connected to the positive terminal, the second is connected to the negative terminal. Here the direction of electric field strength is from positive terminal to negative terminal. So this is the E bar direction. Okay. Here the electrons are moving from negative terminal to positive terminal. Then the direction of flow of positive charge is from left hand to the right hand. So the direction of positive charge carriers is from left to right. The direction of negative charge carriers is minus to plus. Of course, here we consider the metallic conductor. The free electrons are the charge carriers. Hence, free electrons move with the speed negative terminal to the positive terminal, that is opposite to the field direction. Okay. So the first end cross section is AB, the second end cross section is a CD, right? Now the electrons are moving from the this cross section CD plane to the AB plane, that is opposite to the field direction. Okay. So this is, you will understand from the figure. Now, if small n is the number of electrons per unit volume, that is the electron density or concentration of the electrons, the number of charge carriers per unit volume is nothing but concentration or charge density. So here we consider the metallic conductor. Here the charge carriers are the electrons. Therefore, number of electrons per unit volume, we are taking small n. Then the total volume of the conductor, how much? Cross-sectional area into length AN. So for unit volume number of charge carriers N, then the total number of charge carriers in the throughout the conductor would be NAN, right? The electron charge we are taking small q. Then the total charge of mobile electrons in the entire volume of the conductor is given by capital Q is equal NALQ. Here small q is one electron charge. Total number of free electrons in the volume of the conductor NAL into Q. Okay. If T is the time taken by the electrons moving from first end to the second end, this is the plane AB, this is the plane CD. From the first plane to the second plane, T is the time taken by the free electrons. Then how we write the current? Current equal to amount of charge flown by time taken. Q equal to NAL into Q by T, that equal NA into L by T into Q. Okay. So, but the drift velocity Vd equal to L by T. Here the free electron is moving from this second end to this end. So it is covered the distance L length in the time T. Therefore, its drift speed is given by distance traveled by time taken. Vd equal to L by T, that is written here. Okay. Substituting that in the above equation, we get I is equal NAVDQ. Okay. So therefore, from this Vd, you write subject Vd equal to I by A into 1 by NQ. But I by A represents what? Current density. Okay. Then Vd bar equal to J bar by NQ. So this is the expression for drift velocity, and this expression relates between drift speed and the current density. Here n is the number of charge carriers per unit volume. Here number of electrons per unit volume constant. It is the in the order of 10 power 29. For metallic conductors, n value is about 10 power 29 per meter cube. Electron charge 1.6 into 10 power minus 19 coulomb. Here Vd bar direction is J bar direction. The direction of Vd bar is J bar. For electron, obviously we take negative sign there. Okay. Now, the next term is volume charge density. Volume charge density. In electrostatics, we defined the three types of charge densities: linear charge density, surface charge density, volume charge density. Here we are considering the metallic conductor, right? Here the current is nothing but the flow of free electrons, the flow of charge of free electrons, right? So therefore, here we consider the term volume charge density. Since conductor having some volume, the electrons are moving through that volume of the conductor. The amount of charge per unit volume inside the conductor is called as volume charge density. It is denoted with the letter rho. Rho equal to charge per unit volume. So that is we are writing dq by dv or dou q by dou v. So from this dou q equal to rho into dou v, then q equal to volume integral of rho dv, volume integral of rho v. So this is volume charge density rho equal to dou q by dou v. From that we are writing the amount of charge, the total amount of charge flowing through that given conductor having the volume v is given by volume integral rho into dv. Here the SI unit is coulomb per meter cube. Okay. Now, coming to the actual concept that is equation of continuity. So, to discuss about the equation of continuity, since we should know the terminology of current density and the drift velocity, relation between drift velocity and the current density, we talked about all those terms. Now, equation of continuity is nothing but it is a differential equation that gives the relation between current density and volume charge density at a point in the closed circuit. Okay. So for that, you consider the same diagram. Here, a conductor of length L and cross-sectional area capital A. It is connected to the terminals of the battery. The first end is connected to the positive terminal. This second end is connected to the negative terminal, right? So due to the electromotive force of this battery, the current is flowing in this closed circuit, that is I. That the current direction is flowing in this direction, that is from the first end, left end to the second end. So therefore, the direction of electric field strength which is established across the ends of this conductor is capital E, right? The drift velocity of positive charge carriers is parallel to E bar. The drift speed of the free electrons is obviously opposite to the electric field strength. So that is shown in the figure. The electron minus represents electron charge carrier. Electrons flow with the drift speed from the second end to the first end. That is opposite to the current direction. That is opposite to the electric field strength direction or opposite to the current density direction. Okay. Right. So here we are considering a small area element in this cross section. Along this cross section, you assume a small area element ds of this closed surface S, right, which is enclosed the volume V. So this is the total closed surface area, right? Of course, it is the total, the length of this conductor L, area capital A. In this, you consider a small finite volume V. So that closed surface is capital S. On that, again, I am considering the small area element ds across the cross section of this conductor. Then, as per our previous discussion, if dV is the infinitesimal arbitrary volume in a plane and volume charge density is the rho, then the charge in the entire volume V can be written as Q equal to volume integral rho dV. If rho is the volume charge density and V is the total volume of the conductor, right? Then the total charge enclosed by that volume is given by volume integral rho dV, say equation 1. But the rate of decrease of charge at any instant of time going out through that volume is equal to amount of current passing through the conductor at that point. Here it is the concept of law of conservation of charge. So whatever you consider the volume, the closed surface S enclosing some volume V, the amount of charge the amount of charge, the rate of decrease of charge at any instant of time coming out from that volume is equal to amount of current passing through that conductor. So how we understand? So this is a conductor in this I am considering small volume element. Okay. here small volume element. So here the amount of charge leaving through this volume. So the amount of charge coming out from this volume equal to amount of charge, the amount of charge entering into the volume. So here charge is neither created nor destroyed. So whatever amount of charge entered from the first end, the same amount of charge will leave out from the second end. Okay. So therefore here the rate of decrease of charge, the rate of decrease of charge from the second end is equal to the amount of current passing through this conductor. So this is, we are writing according to the concept of law of conservation of charge in the space. That is I equal to minus dq by dt. I equal to minus dq by dt. Let me repeat. The amount of current passing through the conductor should be equal to the rate of decrease of charge at an instant of time, that is leaving that consider the volume. Okay. So I equal to minus d by dt of, but q equal to, we have volume integral rho dv is equal minus volume integral d by dt, right inside of the integral we get dou rho by dou t into dv. This is equation 3. But we have I equal to surface integral of j bar dot ds bar. This is equation 4. So then I equal to surface integral j bar dot ds bar, that equal to, from equations 3 and 4. So here we are writing minus volume integral dou rho by dou t dv. It is equation 5. Then applying the Gauss divergence theorem, the surface integral j bar dot ds bar equal the volume integral divergence of j bar dv, that is del bar dot j bar dv, say equation 6. So then from equations 5 and 6 you can write the volume integral del bar dot j bar dv equal the volume integral minus dou rho by dou t dv. This is equation 7. So from this expression we can write del bar dot j bar equal minus dou rho by dou t. So writing this term left side we get del bar dot j bar plus dou rho by dou t equal to 0. Our divergence of j bar plus dou rho by dou t equal to 0. This equation is called as equation of continuity. Equation of continuity. Here dou rho by dou t, this term will become 0 in the case of static current or steady current. So this equation of continuity is used for varying electric currents. That is del bar dot j bar plus dou rho by dou t equal to 0. That is applicable for varying electrical currents. But when the static current or steady current is flowing through the conductor, so what is meant by static current? If you consider two normal cross sections at point A and B, whatever the amount of current at the cross section A entering, the same amount of current will leave at the cross section B. Then the rate of flow of charge dou rho by dou t remains constant. Then what is constant? Rho is constant. Rho is constant, then dou rho by dou t equals to 0. The rate of change of volume charge density dou rho by dou t equal to 0. Here the amount of current entering at this cross section equal to amount of current leaving at this current. The amount of charge entering at this at the cross section A equal the amount of charge leaving at the cross section B. So like that, if you consider any two cross section normal to the conductor, so then that concept is applicable here. Therefore, we mathematically express it as for the static current or steady current, dou rho by dou t equals to 0. Then the equation of continuity becomes as del bar dot j bar equals to 0, or divergence of j bar equals to 0. So the conclusion is what? For varying electric currents in the conductor, the equation of continuity, we write it as del bar dot j bar plus dou rho by dou t equal to 0, or divergence of j bar equal minus dou rho by dou t. For the static current or steady current in the conductor, since dou rho by dou t equal to 0, then divergence of j bar equal to 0, or del bar dot j bar equals to 0. Hence, the vector j bar is said to be solenoid vector. Here, the charge is not accumulating at any point inside the conductor. If you consider any point inside the conductor, whatever the amount of charge reaching that point, the same amount of charge at the same time, the same amount of charge in the same time should leave from that point. So charge conservation is obeyed there. So for steady current or static current, del bar dot j bar equals to 0. So in the present class, what we discussed is, first we discussed the important terminology, current density concept, that is the amount of current passing through the unit surface area normally at any point across cross section. So J equal to I by E. J bar is the vector quantity. It is measured in the units ampere per meter square. Then the relation between current and current density is written as I equal to surface integral J bar dot ds bar, right? So current is the scalar quantity, but the current density is the vector quantity. The direction of J bar is the direction of drift velocity of the positive charge carriers, or it is opposite to the direction of flow of electrons in the metallic conductor. The drift velocity is defined as it is the constant average velocity attained by the charge carriers when the potential difference is applied across the conductor. It is very small value. It is in the order of 10 power minus 4 meter per second. Here should remember that in the absence of electric field, in the absence of potential difference applied, thermal velocity, average thermal velocity is in the order of 10 power 5 meter per second. When the potential difference is applied across the conductor, then in addition to the thermal velocity, they gain due to the electric field, applied electric field, they are acquiring some acceleration, getting some drift velocity. Drift velocity is very small value. It is in the order of 10 power minus 4 meter per second. With that speed, the electrons drift by following the chord path as shown in the figure. The relation between drift speed and current density is V d bar equal to J bar by NQ. Okay, where N is electron density, Q is the charge of the electron. After that, we discussed about equation of continuity. For varying currents, what is that? Del bar dot J bar equal to minus dou rho by dou T, or del bar dot J bar plus dou rho by dou T equal to 0. If you consider the steady currents or static currents, since dou rho by dou T equal to 0, then we get del bar dot J bar equals to 0. This is the important equations in entrance point of view. The divergence of J bar equal to 0. If the divergence of any vector is 0, then that vector is said to be solenoid vector. Here, you can conclude that the current density is the solenoidal vector. Okay. This equation implies the conservation of charge in the space. Right? Thank you.